In previous classes, we were discussing about the basics of computer vision, and we talked about basically what are image pixels and what is histogram and different spatial filters as well as frequency filters. And then we were discussing about the different key point detectors and descriptors, right? And we just started off with what is texture. So as we were discussing in the previous lecture classes, when you are trying to process an image, right, you can either directly work with the pixel intensity values, or you can try to represent the image in another form. So while you're trying to represent the image in another form, it could be one of the methods could be key point detection and description. So there, in that case, what happens is you're not directly working with the pixel intensities, but trying to find out what are the important points of interest within that image. And then later you can just work with those points of interest alone, right? And we saw about HOG as well as Sept algorithms. Then we moved on to what is texture. So texture is again another way by which you can describe the images. So what texture means is, in simple words, you can assume it to be a pattern which is present in an image which is kind of repetitive. So when you look at an image, at a texture image, you can understand that there is some underlying pattern which keeps repeating throughout. So the human visual system can identify a certain pattern. And so what in computer vision, what we do is, like, especially for texture synthesis, we try to replicate this particular underlying pattern in order to form another image or a larger textured image, say. So we'll be going through some of those concepts in this class. Okay, so we were discussing about different types of texture representation. We can either represent a texture of an image if it's a texture image, or if you're looking at the texture of an object specifically, then we can represent the texture in an object in different ways. So in local texture representation, you can just look at the immediate neighborhoods in order to represent the texture. If it is pooled texture, you look at different image patches and then try to describe the texture which is present in the image. And another type is a data driven, where it is mainly for texture synthesis, that is given an input image with a particular texture, synthesizing another image having a similar texture. So it's not the same image, but having the similar underlying pattern, okay, and synthesizing texture images. And we had also gone through filters used for template matching. So if you are trying to convolve a particular template, okay, so here what you see, let me just, here what you see is a template, let's say, and you have an image. So when you do a convolution of this template with that of the image, you may get an image which looks like this. And here in this particular convolved image or the filtered image, what we see is the points with very high intensity values means that the correlation between the template as well as the image is high, whereas the regions of dark intensities means that the correlation is very less. So this can be used for template matching or identifying a certain specific pattern within an image. Okay, so this is where we stopped last class. We were briefly discussing about what are the different quantitative texture measures. That is, now given an image, there are different methods by which we can try to extract the texture features which are present in the image. And some of the methods, very popular methods are GLCM, GLRLM, loss texture masks, LBP, which stands for local binary pattern, and so on. There are many other texture feature extraction methods, but we'll briefly go through these four techniques in our class. Okay, coming to GLCM. GLCM stands for Gray Level Co-Occurrence Matrix, and here co-occurrence, as the name says, what it tries to measure is it will look at two pixel intensities and see how many times it occurs together in the given image. Okay, so images, as you already know, a particular image, it can be represented in the form of a matrix, right, where all the pixel intensity values are elements in a matrix. So once we represent that, what the GLCM does is it will look at what are or how many, what are the intensities, pixel intensities that occurs together as a pair within the whole image. How many times does it co-occur, or how many times it occurs together as a pair. Like for example, let's say I have a pattern Ij. Now this is done for different directions also. Now let's just take an example of this particular pattern, which is Ij, right? Just 1 minute. Okay, so we have this I and J represent the pixel intensity values. Okay, and here this Ij is the pattern that we are looking for. Okay, and there are two parameters when you're dealing with co-occurrence matrix. There are two parameters here. One is D. Okay, now here as written D represents what is the displacement. That means how much should be the distance between I and j. That is also a factor which is considered. So here what we consider is that the distance is 1, which means that it is adjacent together. Okay, so here this is basically represented by 0, 1. The distance 0, 1, which means that I and j are adjacent together in the horizontal direction. Okay, we'll see the details of that in the next slide. Now, when it is co-occurring together, so this is the pattern that we're looking for. And what GLCM does is, for all possible values of I and j, it will try to calculate a matrix which shows how many times, for all possible values of I and j, how many times it occurs as a pair in this particular pattern itself within a given image. Okay. Now, as an example, so before we move on to the example, just to be familiar with this particular representation. So here C stands for the co-occurrence matrix, and the subscript D stands for the displacement. And this displacement is specified in terms of dr and dc, which is for the distance with respect to row and distance with respect to the column. Okay, that is displacement with respect to the x direction and y direction respectively. Then here I and j stands for the pixel intensity values. Okay, so let us say we have a small image which is given by this particular matrix which is given here, and you want to calculate the co-occurrence matrices. So it is a set of matrices because there are different patterns that can be identified from this particular image, right? So for the co-occurrence matrices, what we can do is we can consider different displacements, okay, and corresponding to different displacements or different directions, we can try or we can find out the GLC matrices. Like for example, as we saw in the previous slide, 0, 1 represents the I and j placed together this way, right? So I is here, j is here. So what this means is the displacement along the rows is 0 and along the columns is 1, right? Now, once we have this pattern, I and j stands for the pixel intensities, and for this particular image, if you look at the pixel intensities, this is just an example image. What we see is there are only 3 pixel intensities, 0, 1 and 2, right? So when we are forming the GLCM matrix over here, what we have is along the I axis we have 0, 1, 2, and along the j I have 0, 1 and 2. These are the maximum possible intensity values that can be assumed by I and j. Now, given this, what we are doing is, for each of these along the horizontal direction, how many times does it co-occur together? Like for example, if I'm considering I is equal to 0, j is equal to 0, that means what I'm considering is if 0 and 0 occurs together, co-occurs together as a pair along the horizontal direction, okay, how many times does it occur together? That entry would be the first element over here. Okay, so if I look at this particular image, what I see is, okay, I see 0, 0 occurring here, 1, 2, 3, and 4. So there are four times that it co-occurs together. So I write 4 here. Now, if I consider I is equal to 0 and j is equal to 1, so if I consider this pattern, okay, along the horizontal direction, I can try to see how many times it occurs in this image. So as you see in this image, it does not occur together, right? You do not have a 0, 1 together in this image. So that would be 0. Now, if I look at 0, 2, that would be 2 times. So I have one here and another here. So I write 2 over here. Okay, so this is how the co-occurrence matrix is calculated, and the remaining entries are also filled. So how many intensities you have, right? According to that, that many would be there. So let's say it's an 8-bit image, you have 256 intensity levels, then that means the possible values of I and j would be from 0 to 255, right? And for that, all the entries are made for calculating how many times the pixels co-occur. Now, this particular example is for the horizontal direction. So same way, this dr and dc, that is the value of d, can vary for different, you can give different values for d in order to find out or identify pattern in different directions. Like for example, if I take 1, 0, it would be in this direction, you have I and j, right? If I take 1, 1, I have in this direction, which is the diagonal. Okay, so for each of these, I can again make the same entries. Like for example, if I consider the vertical ij, and so this one is for I, right? So let me take it as 0, 0. In this case, just see how many times do you, sorry, now this is what vertical, right? So vertical means I have 1, 2, 3, and 4. Again, I have 4 entries here. If I look at 0, 1, again there are no entries with 0, 1, and so on. So like this, we calculate the co-occurrence matrix for different directions, right? And all these matrices which I get, these are all co-occurrence matrices. And what it does is, as I said, it will try to identify a pattern, okay, within different directions. Separately, now you have these matrices. Now, once you have these matrices, so let's say I have calculated for different directions. Okay, so I can calculate for 0 degree, 45 degree, 90 degree, 135 degree, and so on, right? Now, here when I do that, instead of taking the actual values which we have already got, or the entries that we have already got, we can still modify the GLCM matrix before we try to process it further. Okay, one modification is where you can just normalize the GLCM matrices. Okay, so normalizing means just by dividing by the sum of all the entries or all the elements, you can try to normalize that and process it further. That is one way. Or another way is by using a symmetric GLCM matrix. Now, what symmetric GLCM matrix means is, if when I get matrices of this form, okay, that means CD and C minus D, that can be combined together. So what that means is, let's say I have calculated GLCM along this direction as well as along this direction. Both of these can be combined together to form a symmetrical GLCM matrix. Again, this direction as well as this direction could be combined together. So because basically both of them represents the diagonal information, right? So therefore they can be combined together to form the symmetric GLCM matrix. So this is one variation of the actual GLCM matrix, and you can work with the symmetric GLCM matrix. Now, another way is, instead of taking just these directions, that is 0, 45, 90. So after, let's say we have taken a symmetric GLCM matrix, okay, you'll have 0, 45 degree, 90 degree, and 135 degree. Okay, the remaining ones have been fused together with the previous ones. So you have 4 different directions. So either you can work with these, these separately as different directions. But what is most commonly done is, again, the average of all these 4 matrices that together can also be considered. Okay, so either the directional pattern information which is available, or if the patterns which are present in a particular image, if it's more circular or blob-like in nature, then combining all these together may give a better information. So these are different ways by which you can work with GLCM or co-occurrence matrices. Now, once you have this co-occurrence matrix, as we see over here, what we see is it is just another matrix, okay, with some entries, right? So basically what you initially started off with was an image, which is also a matrix with certain elements, the elements being the pixel intensity values, and then you're converting that to a co-occurrence matrix which captures the texture information, but that is also in the form of a matrix, right? So what we do further is, from those metrics, in order to get some quantitative measure from those GLCM metrics, further features are extracted. Different kinds of numerical measures are determined. Like for example, energy, entropy, contrast, homogeneity, correlation, etc. are some of the features that can be extracted from the GLCM matrices, and then we can work with these particular features to further when you're trying to process these texture. Okay, so just be familiar with these terms, okay? Energy, entropy, contrast, homogeneity. So what these measures does is basically it looks at how much similar a pixel is with respect to the neighborhood pixels, or how much pixel, in the sense right now it would be just the matrix entries, right? So, or how much different particular entry of the GLC matrix is with respect to the neighborhood ones, and so on. And with these measures, now it would be after you extract these features, now this set of features can be used to represent that particular texture which is present in the image. So what now what you have is the whole image, which was in large matrix form, has been or the texture in that image has is now defined with a set of features here, right? And it forms a feature vector. So this is one way of how you can represent the texture which is present in an image in a numerical form. Okay, so just to give you an example, let's say this is a particular image that that is given to you, right? And the image can be represented in the form of a matrix here. Now, so this is the image matrix with the pixel intensity values, and you see that there are from 0 to 8 you have the different values, right? So when you're calculating the GLCM matrices, you can calculate for different directions. So you have 0 degree, which takes both 0 1 as well as 0 minus 1 into consideration, right? And similarly you have 90 degree, where you have 1 0 and 0 minus 1 0, which is taken into consideration, and so on. Okay, so you have these 4 different directions, and from which you can calculate what is the total count for each of the co-occurrence that you have, right? And from that you can normalize that, and then calculate what are the different features which are available. You can also combine all the directions together and calculate the various features. Now this set of features that you have would represent this particular image, the pattern which is present in this particular image in the horizontal direction. So this will be specific to horizontal direction, this would be specific to all the directions together, and you can work with just these numbers instead of working on the whole image or the original image as such. So this is the basic concept of the GLCM matrix. Okay, so before we move further to GLRLM, is there any doubts regarding GLCM? Okay, so I assume that you do not have any doubts. Then we'll move on to the next texture extraction method, which is the GLRLM. So GLRLM is also a very popularly used texture method, and it is a very simple method, just like how we have the GLCM. Now, GLRLM stands for gray level run length matrix, okay, or matrices, because you have different matrices for different directions, just like how GLCM is. Now, when it comes to GLRLM, what it looks at is it will look for similar gray level pixel values. That is, given an image, it will look how many the pixels which are having the same intensity values and which are adjacent to each other. So it looks at how many adjacent pixel intensities of the similar intensities which are adjacent to each other, okay, how many are present and at what length it is present. Okay, so and that too along a given direction. Like for example, if I'm considering 0 here, the pixel intensity value is 0 here, so I see that 0, if I look at the run length, so what run length means is the adjacent pixels of the same intensities, how long do they run along the image in a particular direction. Okay, so like that we can calculate. If I take 2 in the diagonal direction, I see that it goes this way. So the count is 3 here, the count is 2 here, and so on. So by looking at how many with the same intensity values, okay, along the same direction, how long it is within the image, you can calculate that number of pixels and form the GLRLM matrix. So when you're forming the GLRLM matrix, let's say it is for 0 degree, that is the horizontal direction. I can calculate along this entry, I have the gray level values, and here I have the run length. Run length is basically what is the number of pixels or how many times it is going. Like for example, here it would be 3 and here it would be 2 and so on. And these entries are made. So here for GLRLM matrix, the number of rows would depend upon what is the maximum gray level intensity which is present in an image. Like for example, in this particular example, you have only intensity values of 0, 1, 2, and 3, and therefore you have only 4 rows here. So if you are taking an 8-bit image, again you'll have 256 gray level intensities, possible intensities, right? And therefore you'll have that many entries in the rows, or that many rows over here. So that would be quite a large matrix, right? And run length means how many times it occurs together, or how many times. So it would depend upon, again, it would depend upon the image, how many number of pixels would be adjacent together. And like this, we will calculate not just for one direction, we also calculate for different directions, 45-degree, 90-degree, and so on. So what we get is again the oriental information along a particular direction, and considering one particular pixel value intensity, how long it is present within the image, and that is calculated. Okay. Now, as I said, if it is an 8-bit image with 256 gray level intensities, it would be a very large matrix over here, right? And then you'll have to further compute all of these entries together. Now, if you're just considering an image, right? Let's say it's an 8-bit image. Okay, sometimes we see that, let's say there is some kind of object over here, okay, and the background that you see is, let's say, the sky, okay, and maybe till here it is the sky region, okay, which is almost homogeneous region. But when you're looking at, since it's an 8-bit image with 256 intensity values, sometimes when you're looking at this, not sometimes, most of the times when you're looking at this image, let's say some of these values, I'm just taking a random number. Let's say one is 128, somewhere else you have 127, somewhere else you have 126 or 125, and so on. So you have, although it represents the same background region, which is the same region, you find that there would be slight differences in the pixel intensity values. And what happens is, if you are looking at a run length metrics, if you are calculating this way, where you're taking each and every value, then what happens is, now these which are present here are considered as different pixel intensities, right? And you have different entries for that. So it would not identify these as one single region, or running along one single direction in this case. So what is usually done is when you're working with either GLCM or GLRLM matrices, it is re-quantized to lesser number of gray levels. So re-quantization to lesser number of gray levels means, let's say you have an 8-bit image with 256 gray levels. Okay, sometimes it may be reduced to maybe 128 or 64 or 16-bit or so on. Okay, so usually I think 64 is used. So it may depend upon what is how many variations are there within the image and your requirements. Okay, so the basic idea here is that it is usually re-quantized to lesser number of gray levels in order to ensure that the homogeneous regions are considered with the same pixel intensity values. Okay, and therefore the gray level entries that you have here, or the number of entries rows that you have in the GLRLM matrix also reduces. Same way in GLCM also, re-quantization is usually done to lesser number of gray level intensities, and then the matrices are calculated. Now, once these matrices are calculated, as discussed earlier, we do not directly work with the entries of those matrices, either the GLCM matrices or the GLRLM matrices or so on. So in GLRLM, the different features which are extracted, I have not included the formulas of any of that because that's not important right now for this course. Just be familiar that there are different features which are extracted, like for example, short run, long run, gray level non-uniformity, run length non-uniformity, and so on. So what this does is, like for example, the SRE, or the short run emphasis, it just measures how many times short runs would occur. Okay, so short runs would be the run lengths, if the run lengths are short, right? So just a few pixels wide. Now, how many such short run lengths are there within the particular image, okay, in a particular direction? So that is what is calculated or measured by the SRE, or the short run emphasis. Long run emphasis looks at how many times you have or how many long runs you have within a particular image, and so on. Then GLN, which is the gray level non-uniformity, it will look at what is the non-uniformity of the gray levels. Or if it is run length non-uniformity, it looks at what is the non-uniformity within the run lengths which is present in the image. There are formulas for this which is not required. Just know that such features are extracted in order to identify what is the texture information in the particular image, and then later it would be with these features that later on you'll be working with these features for further processing. Okay, so another texture method you have is the loss texture mask. Now, this is also quite a little what I say popular, but not as popular as GLCM and GLRLM, but still it is a popular texture mask or texture feature extraction method. Now, in this method, what is done is, 5 one-dimensional kernel vectors are initially defined. Okay, so some of the kernels, or the 5 kernels which are defined, are the level vector, edge vector, spot vector, ripple vector, and wave vector, and the corresponding the vectors are also shown over here. Okay, so if you remember when we were discussing about the edge detectors, right, or edge operators, detection operators, we saw that they're also in the spatial filters. We had used, or we had discussed about different kernel masks where the spatial values or some weighted values are given, and then we do a convolution there. Right. So the concept is similar to that. So here what is done is, there are 5 kernel vectors which are defined. Okay. Now in this example which I've given here, it is 5 pixel lengths long, and these are the values which are there. But it's not always. Now there are also loss texture masks for 3 pixels long also. Okay. So this can vary here. Now 5 pixels, that is most commonly used, and you have these. Now what is done is, these one-dimensional kernel vectors, they are multiplied with each to form 2D kernel masks. Okay, like for as an example, this is L phi and E phi. So as an example, when I multiply E phi and L phi, I get a matrix, two-dimensional matrix as given here. Okay, and I can represent it by writing it as E5 L5, and like that you can do for all that. So some of the like for example, what I can do is L5 with L5 I can multiply, so I get it as L5 L5. Then I can multiply L5 and E5, so I get it as L5 E5, then L5 S5 and so on. Okay, so like that I'll get 25 filter masks or two-dimensional kernel masks can be obtained by multiplying these together with each other, right? Now, from these 25 filter masks, just like how we discussed in the GLCM matrix, right? There are masks which are symmetrical and can be combined together. Okay, like for example, L5 E5 and the output or the filtered image which we get from L5 E5 and E5 L5, they can be fused together to form one image, right? So like that, when you're fusing all the symmetric masks together, okay, what I get would be 15 filter masks would be obtained. And then again, the L5, so basically L5 means it is a, if you look at the previous image over here, 14641 L5, it's called as a level vector. So what it basically does is it will just smoothen out the image. Okay, and if I'm taking L5 L5, it is basically acting as a weighted average filter. Okay, so using this L5 L5, the filtered image that I get would be nothing but a smoothened out image itself. So it is not exactly a texture image which I get from L5 L5. So therefore L5 L5 is usually discarded. Okay, and only the remaining filter masks are taken, two-dimensional filter masks are taken. So like that, totally you'll have 14 filtered images. Now from these 14 filtered images, various features, just like how we discussed in the GLCM, are calculated. Now as an example, this is just an example of how the different outputs of different loss texture masks or the two-dimensional filter masks, the 14 masks that we discussed above, looks like. Okay, so this is for one single image. Okay, so there was one single texture image which had kind of some texture within. Okay, and from this one single image, by using these 14 different texture masks, you see that the different the textures that has been extracted from the image. So what we see is here also, again, by considering different like for example, if you are taking L5 E5, that takes the edge information, or if I'm taking L5 R5, it looks more for repetitive patterns and so on. So various kinds of textures or patterns which are present in the same image can be obtained with different two-dimensional filter masks, as we see over here. Okay, and so one last filtered texture featured extraction method that we are going to discuss in this class is the local binary pattern. Now it is abbreviated as LBP. Now local binary pattern or LBP is it is more recent as compared to the previous three techniques that we were discussing, and it is still now being very widely used. So in the local binary pattern, what is done is, let's say you have a particular image. Okay, so in this particular image, you're dividing this image into different patches or different neighborhoods. Now let's say I'm considering a 3x3 neighborhood. So within the 3x3 neighborhood, I have a center pixel. So what I do is I look at what is the value of the center pixel, and I look at the values of the neighborhood pixels, right? So I basically do a thresholding of the neighborhood pixels, and the thresholded value or the threshold value which I consider would be the center pixel. That is, taking the center pixel intensity as the threshold, I try to threshold the neighborhood pixel. So I get either a 0 or a 1 depending upon whether it is lesser than the threshold value or greater than the threshold value. So what I basically get would be a series of zeros and ones throughout the neighborhood, okay, and that would be the binary pattern which I'm obtaining. So that is why you have the name here, local binary pattern, because it looks at a neighborhood, and binary pattern because it basically thresholds with respect to the center pixel and creates a binary pattern out of that. And now this binary pattern would be the new value which represents this particular center pixel, which means that for after LBP, the image that you're getting, okay, in that image, the new center pixel value with respect to this pixel would represent the neighborhood information. Okay, so like that, it tries to capture all the local texture variation which is present. Okay, now like that we do for all the pixels, and what you get is another image, okay, with all these encoded values, and that one you can call as a LBP map, right? So LBP map would be just another image with all these values. And then what is usually done is a histogram of this LBP map is obtained, and basically this LBP histogram will act as the texture descriptor for this particular image. So just to understand this further, this is an example representation. So let's say I'm this particular image patch or neighborhood, okay, 3 by 3. So let's say this is the image, okay, and from this image I'm taking every 3 cross 3 neighborhoods, okay, and one such neighborhood is this one, and these are the values which are present. So what I'm doing is I'm thresholding with respect to 128, okay. So if I look at this value, since it is greater, I give a 1 over here. Since again here is greater, it's a 1, okay, 1. Here it is smaller, so I have a 0, and like that I am thresholding all the neighborhood pixels with respect to the center pixel intensity. And now after this is thresholded, this particular pattern you have, so that would be 11101001 would be the binary pattern which would represent the center pixel 128, okay. So the decimal equivalent would be 233. Now, like that, you calculate for all the pixels which are present in this image, and when you create a LBP map, okay, it might look somewhat like this. So what we see is that it does not look like the input image, okay, but rather it helps to identify what is the local texture. So each of these pixels has information of what is the local texture description, okay, which is present in the image. And from this LBP map, again, a histogram which is called as the LPP histogram can be calculated or can be determined, right? Now from this histogram you can there are different ways of processing this. So basically this LBP histogram represents the texture which is present in this image, right? So either the histogram features may be extracted, or another more popular way is that, let's say you're comparing two different texture images. So let's say I have another texture image, okay, and I calculate the LBP map and I get another histogram, right? And what is usually done is how similar these two histograms are, or how different these two histograms are, is calculated, okay, in order to identify or recognize the texture which is present in these images. So there are various ways by which this is processed, but LBP histogram is basically the texture description for this particular image. So this is how the LBP, or the local binary pattern, works. Now, in the previous example, what we saw is that we considered a square neighborhood, right? So this is a center pixel and this is a square neighborhood. So instead of a square neighborhood, even circular neighborhoods can be considered. Like for example, okay, I can consider this circular neighborhood. So here it basically looks at the immediate neighborhood which is within, right? So it does not make much of a difference as compared to the previous case. But when you're increasing this radius, you will be able to appreciate what is the difference over here, right? So as you increase over here, so this is the case of radius equal to 2. You see that you consider these only those image image pixels visualized between these particular black spots over here, right? And again, you can keep increasing the radial measure over here. So a circular neighborhood can also be considered for the LBP, for finding the LBP texture pattern, and it has also been widely used for various processing techniques. Okay, so before we go to texture synthesis, now these are the texture feature extraction methods are not limited to these four texture methods that has been discussed, but there are other techniques also which are used, but this one, these are the most popularly used ones, and this would help to give you a better idea of how texture features can be used to describe a particular image. Okay, if you have any doubts till now, I'll take that. Okay, then I'll continue further with our texture synthesis method. So in texture synthesis, as the name says, in this application, what is done is you're trying to synthesize a textured image or another new texture image given a particular texture pattern present in an input image. So what that means is, let's say you are given an input image or an example image with a particular texture, and you want to synthesize another image, okay, with the same texture pattern which is present. So it does not mean that you're trying to generate the same, it is not the same as creating the same, or copy pasting the same image. Okay, it should not look exactly the same, but it should be different. It should have variabilities within the both input images as well as the synthesized image must be having variabilities with respect to each other, but at the same time it should look like as if it belongs to the same texture. So that is the main idea or goal behind texture synthesis methods. And so there are various applications also for texture synthesis methods. Like for example, if there are given an image, if there are some let's say some defects which are present in certain regions within the image, okay, and you want to rectify that. So you can try to, if the texture of that particular region with the defect is known or it is already present in some other part of the image, that can be used as an example in order to patch over. It's like a patchwork where you can try to replace that particular defective region with this new texture region. Okay, so there are various applications where you can use these texture synthesis methods. So as I said, what basically texture synthesis means is, so let's say you have an input image given to you, okay, and you're trying to synthesize a new image. So if you compare between these two images, they are not the same. They are not at all the same, okay, but it looks like as if it belongs to the same texture. It looks like it comes from the same texture image. Like for example, just as an example, it looks like it as if it comes from this particular texture, right? So when we look at these two, we can easily say that okay, this has got the same texture pattern within themselves. So texture synthesis methods, okay, it basically looks at creating or synthesizing a different image as compared to the input image, but at the same time capturing the same texture information which is present over here. And there are various texture synthesis methods for this. We'll be discussing about only one such technique. Okay, so just as an example here, this is an example of an image where a particular region of the image had been pasted over, okay, in order to create the feel of a larger crowd, okay, within a particular campaign. And this had come in the newspaper article also once as a news. So what we see here is that if you if you look at this whole image, it looks like as if there are a lot of soldiers who are within the image. But when you just take a closer look, what we see is see the numbers that you see over here, 1 and 1, okay, it's basically the same person. 2 and 2, it's basically the same person. So what they have done is they have very very nicely replicated all the same patches of information which is present in order to create a larger image. So texture synthesis also works somewhat like this, but it's not the exact same. As I said, it's not the exact same pattern which is taken, but yet the concept here, that is, we try to synthesize a larger image with respect to or given an input image with the same texture. Okay, so when you look at textured regions or texture descriptions, there are different types of classification or categories for this texture. So the texture that you have may be a regular texture, which means that it is a very clearly it is a regular pattern, okay, and you will be able to clearly say how exactly it is repeating, or you'll be able to find the repetitive portion of the image, okay, and see how it goes, right? There are other texture regions also, like for example here we can say that so usually if you look at images of, let's say, some bush or such kind of or a forest cover, let's say. So those are some examples where you see that you can say that there is a specific or there is a pattern, but you cannot specifically say what is a repetitive element over there, right? So such kind of images or textures where it is generated from random variables, you can say it's called as a stochastic. And then there are other texture regions where you have kind of a mix of both the regular pattern as well as the stochastic, okay, so that is also there. Now in texture synthesis methods, in the case of regular, it is quite simple, okay, but when it comes to a mixture of both regular and stochastic, then that would be like it would be a challenge to model or trying to find texture synthesis methods or trying to develop texture synthesis methods that can work with all these variabilities, okay, right from the regular to the random ones. And one term that you can note here is texel. So what texel means is texel is basically the smallest element of the texture which is present in an image, okay, or the smallest element that can be identified as repeating within a particular image is what you call as a texel. So we will be discussing about one very simple texture synthesis method, which is called as the sampling local model. So as the name says, what we do is we just look at the local information, and we do a random sampling in order to ensure the variability is also in the image which is created. And let us see how we can use this sampling local method in order to synthesize a particular texture image given an input image. So let's say you have an input image here, okay, and you want to build up on this input image to create a larger image, okay, with the same texture. So in order to do that, you can use the sampling local model, which we'll be discussing right now. So what we'll first see is, so let's say you want to calculate for 1 pixel. We'll take the case of one single pixel. That is, if you want to find what is the value of this one single pixel in the new or in the larger image, that has to be synthesized, or the new value has to be found out. What we do is we look at the information which is present within this input image which is given to us, and then by taking this information into consideration, we try to synthesize or give a new value for this new pixel over here. So we'll see how it is done. Now we'll take the same example as before. So let's say this is the input image we have, right? This is the input image, okay, with a particular texture which is given to us. Okay, let's see. So okay, or let's do one thing here. Let us consider this as the patch, okay, and let us take this as the input image. And I want to create a larger image. So here I'm not taking this one here. So let's say this particular image belongs to this region over here. Okay, so this is this particular image. Let's say, just imagine, okay, because I wanted the border value here from which I'm going to build upon and create a larger image. Okay, so let's say this is the image patch which I have considered, and I'm just taking the case of synthesizing 1 pixel at a time to create a larger image. So if I'm synthesizing just 1 pixel, I'm considering only 1 pixel over here, and I want to find out what is the value that I can give to this particular image pixel, and then like that I do for different pixels and try to create a larger value. Okay, so in the sampling local model, what is done is this particular patch, let's say I'm representing here, and this is the pixel whose value I need to find out, right? So what is done is, again, let me just consider this as a it could be a 3x3 or 5x5. So you can consider any image patch over here. So this particular patch of a given size, what I do is, I will, in this image which is given to me, I will try to find out all the possible input patches which are present in this particular image of the same size as that of the input patch which I'm considering, and I compare what is the similarity of all the patches which are present in this image with the input patch over here. Okay, I try to see how similar each of these patches. So I am trying to divide this. So let's say this is one patch, this is another patch, then I have another patch. Okay, it could be overlapping patches, it could be non-overlapping patches, or so on. So if I'm considering, let's say, overlapping patches, and I am considering all these patches, each patch which I consider, I try to compare with this input patch. Let me call this as the input patch, and then I try to see how similar it is to the input patch. Okay, and like that I will compare for all the input, all the patches which are present in the input image. Now, after comparing that, so there will be a certain similarity measure which would be used to find out how close or similar it is with respect to the input patch. Now, once I do that for all the image, or for all the for all the patches which are present in the image, I select a few of the best similar or most similar patches, or the best matching patches. So let's say for this particular patch, now I have identified 4 different. Okay, so just taking a random number, let's say I have identified 4 different patches, okay, from this image which is very similar to this particular input patch, right? So after I select a few of the closest matches as that of the input patch, or most similar patches as that of the input patch, what I next do is I randomly select one among these. Okay, I just randomly select anyone. So let's say I'm selecting this one. Okay, so once I select this one, what I do is, now I need to find out what is this pixel intensity or value over here, right? So corresponding pixel intensity value which is present over here, that would be replaced in this particular pixel value. Okay, so here one thing you have to note down is, we are not looking at the best performing or the most the best match with respect to the input. I can select what is the best match over here and then calculate or find the value over here, but I'm not doing that. The reason why you're going for the top few best matches and then randomly selecting one among that is so that you ensure there is some variability in the image which is being synthesized. No, it is not just one pixel. You keep on building upon all the pixels, and create the larger image, right? So in that case, if we look at only the best match and then try to build upon this given input patch, what happens is the possibility of this, looking very similar as that of the input image would be very high. Okay, but you do not want it to look exactly the same as that of the input image. You want it to have some variabilities, right? But at the same time, you also want to ensure that the basic texture which is present in the image is also retained. Okay, so for that, what you're doing is you're for getting that variability, you select a few of the top best matches and then randomly select one of them and then select that particular or replace for that particular pixel intensity, okay, or a new pixel value. Now, this is the case if you are considering for one single pixel. So, if you're taking for different pixels or more than one pixel, we'll see how it is done in the next slide. Okay, so just to give you an example now, here when you're considering the size of the neighborhood, so in the previous slide, I have mentioned that we look at this neighborhood and this size, it can be 3 cross 3 or 5 cross 5, or it can be a much larger, patch that you are considering, right? Now, the size of the patch that you are considering is also very important. Okay, so the size of these patches that you're considering is also very important when you're trying to create another image. Like, for example, and this is an example which shows how the size of the neighborhood is important when you're trying to synthesize an image. Like, for example, let's say this is the input image which has been given to us. So what we see is there are circular objects which are present in the image, and we also see that there is a certain it is kind of equidistant from the centered circle, right? Or or with respect to each other. Okay, it is kind of equidistant. It's not exactly equidistant, but it is equidistant with respect to the centered circle we see. So what we see is that there is both shape information over here, that is the objects that we have here are circular, and we also have a distance information, in the sense there is a specific distance pattern which is present with respect to the objects, okay, with respect to each other, right? Now, when you're selecting the neighborhood, okay, so what we do is that we are trying to synthesize a bigger image, okay, from or given this particular image, right? So let's say you're considering this particular, this is the same image, just zoomed, okay. Now, if I consider this particular patch, this blue patch, which is shown over here. Now, what we see is that in this blue patch, okay, that means this is the input image which is given, right? And this blue patch represents what is the neighborhood that you are considering, right? From which you have to create a new, so this would be the synthesized image, okay, which has to be created, right? So if I'm considering a neighborhood like this with the blue color, what you see is this neighborhood captures only a partial information with regard to the shape of the object. That means the whole circular object is not present within the neighborhood. Only a partial of the circular object is present. Okay. So what happens is, now if you're trying to use this particular neighborhood in order to create the synthesized image, since the whole of this circular pattern is not captured within the neighborhood, it will try to create such kind of region. So you have only this semicircular kind of region, right? So accordingly, only these kind of regions would be created in the synthesized image, and that is why you get a synthesized image which looks like this. Now, if you compare this synthesized image, okay, with this particular example image which has been given to us, what happens is, now this is not exactly the kind of texture that we were looking for, right? So this particular texture has not been captured or has not been generated within the synthesized image. Okay, now let us say that we are considering a slightly larger neighborhood where the whole of the circular object is present within that patch or the neighborhood that we are considering, right? So here it now considers the whole of this circular region, and you're trying to synthesize a new image with respect to this particular neighborhood. So what happens now here is you see that there is an image which is generated with the circular objects. Okay, it has been generated. So you see here there's a circular object, here there's a circular object. So all these has been created. But it is not exactly the same as that of the example image. Why? Because the distance information, okay, it is not exactly equidistant from each other. The distance information has not been captured by by this particular neighborhood that has been considered. So even though you get the circular objects within this particular synthesized image, you see that it is not exactly the same pattern that is represented by the example image. Okay, so that means this neighborhood is also not good enough for generating this particular example image. Now let's say I'm considering a slightly larger neighborhood, the red color one, right? So in the red color one also, it is slightly larger than this neighborhood, but still in the red one also you see that still you have only the circular object. You have the circular object, and at the same time it also gives the information that okay, certain distance, okay, from this till here is still blank. So what you see is again you get an image, okay, which is kind of regularly spaced, okay, kind of, but not exactly equi spaced as seen in the example image, right? So if you consider this purple patch over here, what it does is it has both the circular object, okay, as well as a partial region of the next circle also, okay. So if you consider this purple neighborhood, the synthesized image you get would be like this. So why you get circular images with a very regular or equispaced pattern and similar to the example image as we see here is because it has got the information that you have circular objects, okay, and you have this distance information also, which is captured, the distance between this object and the beginning of the next object, that has also been captured by this neighborhood over here, okay, and that is why you're able to get a much more closely looking or better looking synthesized image with respect to the example image. So here the main idea or the point here is that the size of the neighborhood that you are considering is also important. Okay, so given a particular image, if it has got certain distance information or a distance pattern, okay, which is present and it's not just the shape, then you need to decide on a size for the neighborhood, which would also ensure that this particular distance information is also captured or represented by the neighborhood along with the shape of the object. So this is just an example that shows how it's important. And in this slide, what we see is just some other examples. So this example has been discussed in the previous slide. These are again other examples where you have this as the input or example image, okay, and if you're considering a very small neighborhood, okay, we see that this particular regular pattern has not been captured, okay, and as the size of the neighborhood increases, you see that there would be a better pattern which is obtained. And similarly, if you're looking at this brick image also, you see it becomes better with a larger neighborhood, okay. And here the size of the neighborhood plays a very important role, especially if you have a very regularly occurring pattern with with a specific distance information with it. Okay, so as we discussed in the previous slide, when we were discussing about sampling local model method, right? We said that what we do is from the example or from the neighborhood that we are considering or the input patch that we are considering, okay, We look at all the patches within the image, right? So, and we look for a certain measure of similarity here, right? So the measure of similarity that we are, which is commonly used, is the SSD, or which is called as the sum of square difference. And this is the, okay, sorry, you have, okay, yeah, sum of square difference. So what is done is, here we take the sum of the square of the difference. So here Aij and Bij are basically the pixel values, okay, which are present in both the, so A can be represented as the new patch, and B is the patches, or all possible patches within the image, and the difference is taken, the square of the difference is taken, and it is summed over all values of I and j except for ij equal to 0 0, if we consider this 0 0 to be the location of the new pixel which has to be generated. So what that means is, except for the region of the new pixel, for all the other regions the SSD is calculated and it is measured. Okay, and this SSD is used as a similarity measure to see how similar the different patches in the image is with respect to the input patch, and then we select the most best matching patches, and then select randomly one of them. Now, yeah, here one variation of the similarity index, or the function that can be done is, you can also use a weighted averaging over here. Okay, and what you're doing is, you can give you can just multiply that with a Gaussian distribution over here. So what we are doing is basically doing a weighted averaging for the SSD. So that is one improvisation of the SSD method, okay, to give better results. Okay. Now, let's say you want to synthesize more than one pixel. Okay, so you have a few pixels that need to be synthesized together. So what we do in such cases is, when you're taking the similarity function, what we do is, now if it was just one pixel, we will discard that particular pixel and average over all the other pixels, right? So here, when we are synthesizing for more than one image, or sorry, for the more than one pixel, all those new pixels that has to be synthesized would be discarded, and the remaining ones, okay, only the remaining ones would be averaged over. Okay, and it is normalized over. You can also take a weighted averaging for the similarity function. So the similarity measure that is used is modified. Okay, so this shows a pseudocode of how the sampling local model works. You can have a look at it. It's the same as that has been explained over here. So this can be called as this is the algorithm, or the pseudocode for the sampling local model, and it is also called as a non-parametric, is a non-parametric texture synthesis. Okay, so coming to further examples here, so let's say you have this image, and by sampling local method, you see that it is justified, right? You have a fairly good looking synthesized image over here, which looks similar to that of the example image. So in this case also, it works fairly well. Here also, you see that it works fairly well. Now, if you look at this particular example, so what is the example image which is given to us is basically a text image, right? Now, if you're using a text image, okay, which to be or synthesized over here using the sampling local model, you see that this is one example of how the output looks like. So it looks like as if if you just look at it, okay, without trying to read it out, we see that we feel like it has done a good work in synthesizing another text image. But if you look closer, what you'll see is that you cannot, these are not really words over here. Okay, you cannot, it does not make any sense over here. Now, so what happens is, in the sampling local model, it will just look at the pattern and then try to create or synthesize an image. Okay, it does not look anything beyond the particular pattern or the distance information which is there. Okay, so there is no parameter here to describe whether the text makes any sense or not. Okay, there is no such method or thing which is done over the sampling local model in order to create the text. So when you're creating text images or synthesizing text images, you need to ensure, or you need to put in a constraint, or you need to develop methods, okay, wherein it also ensures that the text over here, okay, or the words here also makes sense. So just an example to show that although it works for the texture images in general, for text images which contains words, this does not work well. Okay, so before we go to ransack, if there is any doubts so far, I'll take that. Okay, now we'll go to the ransack method. So ransack is nothing but a random sample consensus. Now this is basically a method wherein we try to identify the outliers which are present in a particular distribution. So what that means is, let's say you are given a distribution of points. Okay, so let's say you have an image and then you're trying to calculate the gradient of the image. Okay, so when you're calculating the gradient of the image, what you basically get is the edge information of the different objects which are present in the image, right? Now, given these gradient points or the edge points, okay, let's say it you want to identify a particular, or you want to fit in a particular model to that. Okay, so basically all these points were, you can say it appears to arise from a particular model, right? And you want to fit in a model that best fits this particular distribution of points. Now, what happens is, if there are noise which is present in the image, noise being a high frequency component in the image, or noise being, it has got a high contrast with respect to all the, usually with respect to all the neighborhood pixels, what happens is noise is also misidentified as edges, right? So when you're trying to take a gradient image, or when you're using the edge operators along with the edge information, you may also have the noise pixels which has been detected. Okay, now in such cases the noise pixels would act as the outliers for us. So basically outliers, what it means is those points which are not arising from, which appear to be, or which are present within the distribution of points that you are having, but it really does not appear from or arise from the particular model that is the underlying model which is represented by the distribution of points. Okay, so we'll just look at an example what it actually means. So let's say you have a distribution of points which is given like this. Okay, now here if you look at these points over here, most of these are concentrated within this region. So you can say that it is more or less, you can fit a line to this, and you can say that all these points belong to this particular line or belongs to this particular edge. Okay, and in this case here, these as well as these points are the outliers with respect to this particular line fitting model that we are considering. Okay, so in this example, let us see how the ransack algorithm is able to identify these outliers. So in the ransack method, what is done is it first tries to find out what is the minimum number of points which are needed to represent a particular model, okay, or in order to fit a particular model. So in the case of a line, you just need 2 points, right? So if it is a circle or an ellipse or any other shapes that you are considering or any other models that you are considering, the degrees of freedom differs and the number of points which are required also differs. Let us take the simple case of a line fitting model, right? So if I'm taking or considering the model to be basically a line and given a distribution of points, what you're trying to do is you're trying to fit the line or find the best estimate of the line in the distribution, and with respect to that we are trying to identify what are the outliers which are present, right? So in the ransack, when you're doing a line fitting model, the minimum number of points that we require are 2 points, right? So what ransack does is first it will just randomly select any 2 points. So let's say randomly it has selected these 2 points. Okay, so just randomly select 2 points. Now with respect to these 2 points, it will try to draw a line or create a line. Now, once a line has been fitted with respect to this particular two random points which has been considered, okay, so I'm trying to fit in a particular line over here. Next, what is done is a particular threshold value is determined over here, okay, with respect to which, so this that particular threshold value, okay, which we represent as delta, that is used to represent, okay, what are the inliers. Inliers are points which are part of the same distribution or which appear to arise from the same distribution, right? So all the points which lie within the region plus or minus delta with respect to this particular line are called as inliers, okay? And all the points which lie outside this particular thresholded region or this particular area that we are considering would be called as the outliers, okay? So for this particular model, that is what we have done is first randomly select 2 points. We fitted the line for that, right? And then by determining a particular value of delta, you can try to find out how many inliers are present and how many outliers are present for this particular model. So let's say this for this particular line estimate or model 1, you have it this way. Now this process is repeated. So here for the previous example itself, let's say I'm considering this value delta over here, right? These are the 2 random points which were considered, and after specifying a delta and determining this particular region, the blue color points over here would be the inliers, okay, and all the remaining ones, the red points, have been identified as the outliers. So in this case, we note down how many inliers are present and how many outliers are present for this particular line estimate. Now next what is done is you take another 2 random points, okay, and for those 2 points again try to fit in a line, okay, and take the thresholded region or the region of interest from there and identify how many inliers and outliers are there, okay. So with respect to here, now if there is another line estimate, you've tried to find out how many inliers and outliers are there, okay. Again you randomly select 2 points and try to find out how many inliers and outliers are present. So like that, this is repeated. Now, for example, the finally like one of the best fitting model which you get would be this one. So how do you find the best fitting model? So let's say you have considered a few iterations. So for each iterations you have random 2 points and you have fitted the models and you found the inliers and outliers, and this is repeated for a few iterations. Now from among all these we try to find out the model which has got the maximum number of inliers, okay. So what we are saying is the best fitting model or the best line estimate would be the one which has got the maximum number of inliers. And let's say it is one of the models, and let's say it was model 3 with the largest number of inliers with respect to all the other models. So then this would be considered as the best fitting model out of all these, right? And so for this particular example, this would be the best model. Okay, so let's say these two were the random points that were considered. Anyway, the best model with respect to this particular data point distribution given in this example is this particular line. Okay, and we see that in this region of delta, the maximum number of points or the inliers which are present is larger, right? So after finding the best fitting model and the one with the maximum number of inliers, that would be decided as the model, the basic underlying model distribution, and the corresponding outliers are identified as the outliers, and these can be discarded before we process the images further, or the gradient information or the points further. Now, why this is important to identify the outliers is, let's say as we discussed in the previous example, let's say you have the noise pixels present, and what you're trying to do is, given the edge, the gradient information, let's say you're trying to fit in a particular circular shape, or an elliptical shape, or we are trying to find out what is a particular specific shape of an object. Okay, if you have noise pixels or noise edges, undesired edges or noises which are present in the image, it would affect with trying to find out the best model for that. Okay, so what we do is, now not just in images, in other cases also, when you have outliers, okay, when you further process the images, you may not get the desired output with respect to the because if you're using for post processing or for later processing, if you're using image or if you're using techniques which are heavily dependent on the data samples which are being used, right, then in such cases the outliers would create a problem. Okay, so that's why it's important to identify the outliers and remove the outliers. So that is basically the ransack method, okay, random sample consensus, and this is the pseudocode for this method. So you can go through the pseudocode and try to understand the basic steps in the pseudocode for ransack algorithm. Okay, so here now certain points, certain things is that the number of samples which are present, you need to have, in order for ransack to work well, you need to have a fairly good amount of data sample points which are available in order to represent the particular model distribution. Okay, otherwise then if there are more noise pixels than the actual information which is present, then it wouldn't work. So you need to have a sufficiently good number of sample points which represents the model distribution to be present in the particular image that you are considering. Okay, then another point is the value of delta that you're considering. Okay, so there also that also determines what are the inliers which are present, right? So considering how much the point should be close with respect to the fitted line or the fitted model is also important. So these are the some of the points which has to be, or which can be fine-tuned, or which has to be taken care of when you are working with the ransack algorithm. Okay, so if you have any doubts so far with any of the topics that we have discussed, you can ask me now. So what we started off with was, we looked at certain texture feature extraction methods like GLCM, GLRLM, loss texture masks, and LBP. And then we moved on to, or we discussed about a texture synthesis method using the local sampling model. And the last topic for today's class was the ransack algorithm, where it tries to identify the outliers which are present in a particular distribution, point distribution. If you have any doubts, you can ask me now. Okay, in the next class, we will be learning about the affine and Euclidean geometry, the basic concepts of that, and then we will move on to image registration. Okay. I've downloaded the attendance. Thank you.
Thank you, ma'am.